introduce our first speaker, who's Anton Burkov from the University of Waterloo and Perimeter Institute. And he's going to talk about unquantized anomalies in topological semimetals. So looking forward to your talk, Anton.
Thank you, Adolfo, and thanks to all the other organizers for inviting me to this workshop. It's a really great lineup of speakers. I enjoyed all the talks yesterday, and I look forward to all the other talks. So I'll talk about unquantized anomalies in topological semimetals. Let me first thank my collaborators. Lei Yang. She's a grad student at Waterloo, and she's a joint grad student with Chong Wang, who is a faculty at Perimeter. And so most of the work was done with Lei and Chong, and some of the work that I may mention at the end of the talk was also done in collaboration with Manisha Takurati, who is my former postdoc and currently at Indian Institute of Technology, and Dancy Hayek, who is a grad student at Waterloo. So this is the outline of the talk. So the first part of the talk will actually be about the unquantized anomalies in topological semimetals. And in the second part, if I get to that, I'll talk about something that's closely related, basically a strongly correlated state in magnetic wire semimetals that preserves the anomaly, that preserves the chiral anomaly in magnetic wire semimetals, and that's a generalization, a non-trivial generalization of the fractional quantum Hall effect to 3 dimensions. And so these are the references for the material in this talk. So, well, since the organizers asked us to be provocative, let me start by asking this provocative question. So what is topological? What is actually topological about topological semimetals? And well, the standard answer that's usually given is in terms of topological invariance in momentum space. And well, let's say in the simplest case for a wire semimetal, this is the Chern number of a sheet of the Fermi surface that encloses a single Weyl node that's given by the flux of the Berry curvature through that Fermi surface. Now, this is fine, this is correct certainly, but the problem is that this picture relies on non-interacting band eigenstates, and therefore this is generally not applicable with interactions, in particular with strong interactions which cannot be treated perturbatively starting from non-interacting band eigenstates. Now, as you all know, a more general picture of topological phases in general is in terms of response. And a topological response, an example of that is the anomalous Hall effect in magnetic wire semimetals, where the conductivity is proportional to just the distance between the nodes. But the problem with this is that other kinds of topological semimetals, like non-magnetic wire or Dirac or nodal line semimetals, don't really have any obvious topological response of this kind. And so this raises the question: does it mean that that other topological semimetals, excluding the magnetic wire semimetals, are not really topological, quote unquote, in any real sense, once the interactions are included? Okay. And well, as I will show in this talk, the answer is no, they are topological, but the corresponding topological responses are just still more subtle than in magnetic wire semimetals. But so to set the stage and to introduce some of the concepts that I'm going to use, let me actually start by explaining how this works in magnetic wire semimetals. So let's suppose I have the simplest magnetic wire semimetal with just 2 nodes, on the z-axis at kz equals q and minus q. And so then, as you all know, this is characterized by a Hall conductivity, sigma xy, that in natural units, which I will use throughout this talk, so h bar equals c equals 1 always. So in natural units, the Hall conductivity is equal to 1 over 2 pi. So the two-dimensional Hall conductivity quantum times 2q divided by 2 pi. And this is basically just the ratio of the distance between the Weyl nodes to the reciprocal lattice vector, to the size of the Brillouin zone along the z-axis. And so in the non-interaction or in the weakly interaction case, by Wiedemann-Franz law, there is the corresponding there is also the corresponding thermal Hall conductivity, which is just proportional to sigma xy with this coefficient. And so, so I can express the existence of this Hall conductivity in terms of this kind of term in the effective action for the electromagnetic field when the fermions are integrated out, which looks like a Chern-Simons term, except it's in 3+1 dimensions. And so, this action is usually regarded as describing the chiral anomaly. Now there are different ways to understand to describe what the chiral anomaly is. So let me here give you a viewpoint that's not often presented. So what's anomalous about this action is that it's not invariant under large gauge transformations. So what does this mean? So suppose I make a gauge transformation of the temporal component of the gauge field. So I send A0 to A0 plus d tau chi. And so in principle, chi, it's consistent with anti-periodic boundary conditions for the fermions along the imaginary time direction, that the integral of the time derivative of chi can be any integer multiple of 2 pi, right? And so this is called the large gauge transformation. And you can see easily from this action that under such a large gauge transformation, the action actually changes by a non-trivial phase factor if 2q is not equal to a reciprocal lattice vector. Okay, so what this means is that the action is not invariant under large gauge transformations, and this is of course a problem. It should be invariant, right? What this means basically is that there have to be some gapless modes that compensate for this gauge non-invariance of this action. Okay. Now these gapless modes can come from the Fermi surface, but these can be excluded by filling, right? If I have an even integer filling per unit cell, then there is no Fermi surface, and this basically leaves only one possibility, which is the Weyl nodes. Okay, so in this way, this chiral anomaly with a coefficient that's not proportional to this action with a coefficient that's not proportional to a reciprocal lattice vector basically makes the Weyl points necessary in the weakly interaction case. Now, there is another consequence of this action apart from the Hall conductivity, and that is that, as you can see easily from here, if I consider a 2 pi flux line, and 2 pi in natural units is just the usual flux quantum, hc over e. So if I consider 2 pi flux line along the z direction, then it follows, this action tells me that this 2 pi flux line carries a charge, that's total charge that's equal to 2q divided by 2 pi times Lz, so the length of the system in the z direction, or charge 2 pi divided by 2q 2q divided by 2 pi over d per unit cell, where d is the lattice constant in the z direction. Okay. Now, this is equivalent basically to saying that that the YL semimetal has this special 0th Landau level that crosses the Fermi energy at the location of the YL points, and this charge is simply the filling of this 0th Landau level. And this picture is usually what is used to describe what the chiral anomaly is, right? The pumping of charge from the left to the right node in the presence of the linear electric and magnetic field. Now, but so what's important for my purposes is that this fractional charge per unit cell is in a sense a more topological quote unquote property than the Hall conductivity, because the three-dimensional Hall conductivity is actually non-universal, unlike the Hall conductivity in 2 dimensions, right? It contains this length scale, the lattice constant in the z direction. It has to contain it basically by bidimensional, just bidimensional arguments, but the charge is a simple number, right? Well, of course, you know, in this case of a magnetic YL semimetal, saying that I have this fractional charge per unit cell is basically the same as saying that I have a fractional Hall conductivity, 2-dimensional Hall conductivity per atomic plane. Right? This is the same thing. However, the point is that unlike the Hall conductivity, this property, the fractional charge on a flux line, this is actually, as I will show, is actually generalizable to other topological semimetals. Now, so even though this fractional charge per unit cell is itself a topological property, this action is you know, manifestly non-topological. This doesn't look like a topological term, not just because of the presence of this length scale, but also because, you know, there is a this cannot be written in a coordinate independent form, right? There is a preferred direction here, z. And so I want to write this action as in the form of a topological term. And what I can do here is consider a deformed YL semimetal, a deformed crystal. So this basically means that I send 1 over d to 1 over d delta mu z minus minus d mu uz, where uz is the atomic displacement in the z direction. So this deformed YL semimetals or inhomogeneous YL semimetals have actually been discussed in recently in a very nice series of papers by, you know, some of the participants of this workshop and one of the organizers of this workshop. But so what I want to do is go a little bit further. So I want to account now for the fact that the atomic position is only defined modulo a primitive translation, which will allow me to talk about topological defects in the crystal symmetry, which are dislocations. Okay, so this can be accounted for basically by changing d mu z to d mu uz plus an integer z mu, right? And so this basically allows the integral of d mu uz of the strain tensor around a closed loop in the sample to be not equal to 0, but to be equal to an integer, and that integer is just the number of dislocations, dislocation lines that cross this loop. Okay, so this viewpoint has also been discussed in a number of recent papers. And so now let me leave in the, so this integer now, I'm going to call this a translation gauge field. Okay, so this will contribute to this action, and I'm going to focus my attention only on the topological part of this action, which involves only the translation gauge field. Okay. And so then I can write this action now in this manifestly coordinate independent form using the wedge product notation. And the coefficient now is this precisely this number, the charge per unit cell. Okay. Now, so this translation gauge field is basically defined. The gauge invariant quantities are Wilson loops, right? So the circulation of the gauge field Z along the Z direction simply tells me gives me the number of unit cells, total number of unit cells in the sample along Z. While the integral of Z along the transverse direction, so basically X, Y, and this should be imaginary time, gives me a shear of the periodic boundary conditions in X, Y, or T along the Z direction, okay? And finally, the integral of Z around any closed loop gives me the number of dislocation lines enclosed by that loop. Okay, so these three are the only gauge invariant quantities associated with Z, but Z is a true gauge field. Okay, so let's now take this and try to generalize this to other topological semimetals. So let's start with Dirac semimetals, in particular with type 1 Dirac semimetals. So these are materials that have a pair of Dirac points at two non-trivial momenta on an axis of rotation. So and the gaplessness of the Dirac points is protected by rotational symmetry, by crystal rotational symmetry. Let's take that symmetry to be C4 for concreteness. It doesn't have to be C4, but let's just choose C4. Now, so here, I mean, the reason that a translation gauge field appears in the action for the wild semimetal, that translation and the electromagnetic fields appear in the action for the wild semimetal is that basically the gaplessness of the wild points is protected by two symmetries, the charge conservation and the translational symmetry. If I break translational symmetry, I can hybridize the nodes and gap them out. If I break charge conservation symmetry by creating a superconducting state, I can also gap the nodes out. So from this viewpoint, the topological term that characterizes the response of a Dirac semimetal should contain three different gauge fields. It should contain the electromagnetic gauge field, U1, which I call U1, translation, because the gaplessness here is also protected by translational symmetry, and the rotation gauge field. Okay, and well, to find the topological term, I'm going to use the process that kind of a reverse of what I presented for the magnetic wire semimetal. So in that case, from the form of the topological term, I inferred the existence of this zeroth Landau level, right? And this fractional charge per unit cell was just the filling of the zeroth Landau level. Here, I'm going to use the reverse process. I'm going to find the zeroth Landau level for the Dirac semimetal, and from its properties, infer the form of the topological term. Okay. So, well, so this is what the zeroth Landau level for a type 1 Dirac semimetal will generally look like. It basically looks like a pair of lowest Landau levels for two time-reversed wild semimetals. Okay, so they cross, and normally a gap would open up, but what protects the crossings here is the, in our case, C4 rotational symmetry. Okay. So also this is the rotation operator, and basically the point is that those two Landau levels have different eigenvalues of the rotation operator, and with this particular definition of the rotation operator, I just multiplied it by this phase factor for convenience. with this definition of the rotation operator, the eigenvalues are basically 1 and -1. And I can associate a rotation charge to this of 0 and pi, okay? And so you can just see from this picture basically that the ground state of a type 1 Dirac semimetal in the presence of magnetic field is characterized by a non-trivial rotation charge. And this non-trivial rotation charge is proportional to the distance, proportional basically to the same quantity as we've already encountered in the case of magnetic wire semimetal, which is just the ratio of the distance between the Dirac points to the reciprocal lattice vector. Okay, and of course the number of flux quanta, which is the number of orbital states within the lowest Landau level, also enters here. And so given this, I can basically immediately write down the topological term. So I'm going to introduce now a rotation gauge field, which I will call small c4, okay? And so physically, the rotation gauge field just accounts for the fact that you can locally rotate coordinate axis by any multiple of pi over 2, right? And so the temporal component of this rotation gauge field, by definition, couples to the rotation charge, right? And so from this, from the fact that I have to get this rotation charge in the presence of magnetic field, basically this is the topological term that corresponds to this. Okay. Well, the rotation gauge field is basically defined by the property that for any closed loop, the circulation of this gauge field gives me the number of elementary pi over 2 disclination lines crossing the loop. Okay. Now, well, if you are still confused about where this term comes from, there is a kind of a simpler way to think about this. So I can look at a low energy theory of the Dirac semimetal, and in that case, it may be just viewed as a pair of time reversed Weil semimetals, and there is a exactly conserved quantity in this limit, which is just the z component of the spin, and so this discrete rotational symmetry, C4 rotational symmetry in this limit simply becomes a continuous spin conservation symmetry, right? And so I can simply introduce a spin gauge field with charges pi and 0, right, corresponding to those two different eigenvalues, and just simply add this additional gauge field to the actions of the 2 Weil semimetals that we've already discussed, and simply subtract them, right? And that's how you get this term. And then I have to remember that this symmetry is not really continuous, but a discrete rotational symmetry. Okay. Now, so this action has the same property as the topological term for the Weil semimetal, namely it's not invariant under large gauge transformations. So in particular, it's not invariant under the transformation of this rotation gauge field C4, right? Since it's C4 rotation, so rotation by 4 times pi over 2 is the same as no rotation. So this has to be so a gauge transformation of this C4 gauge field is basically C4 going to C4 plus 4 times any integer, okay? And you can see easily from this that the action changes by this phase factor, which for a general separation between the Dirac nodes is a non-trivial phase factor. And again, by the same logic as in the case of wild semimetal, this makes gapless Dirac points necessary, except for, actually for certain values of the separation. For example, when nu equals a half, which corresponds to the separation between Dirac points equal to exactly half of the reciprocal lattice vector, this phase factor is actually trivial. And so this implies that there is no anomaly in this case, and the Dirac points can actually be gapped by interactions. But let me not go into this. This is discussed in our paper, which you can look at. Now, well, so the non-trivial consequence of this action now is that a disclination line along the z direction carries a non-integer charge per unit cell, as again can be seen from this action. If I just move the d to C4, right? And so this non-trivial charge per unit cell on a disclination line is the analog of that charge per unit cell on a 2 pi flux line, on a 2 pi electromagnetic flux line in the magnetic wild semimetal. Okay, so this is the non-trivial and in principle observable response, topological response that characterizes a type 1 Dirac semimetal. Okay.
5 minutes.
Okay. Well, so let's now talk about the time reversal invariant wild semimetal. So this can be obtained from well, the simplest model for a time reversal invariant wild semimetal may actually be obtained from the type 1 Dirac. Just by breaking rotations and inversion. So this splits the Dirac points into two pairs of wild points. And so we can again play the same game. I can look at the lowest Landau levels, and this is what they look like. So there is again a pair of lowest Landau levels. They don't cross each other in this case, but they do cross the Fermi energy. And if you stare at this picture for a moment, you will realize that the important property that this has is that this is characterized by a non-zero total momentum. Okay, and this not there is a non-zero total momentum in the ground state in the presence of the magnetic field, and this is allowed by symmetries, right? If I break inversion and in addition apply magnetic field, I can have a non-zero momentum in the ground state. This does not mean the non-zero current, of course, right? Current is not the momentum. Current is proportional to the velocity, but a non-zero momentum is possible. And the coefficient here is related to basically the separation, both the separation between the individual wild nodes and also the separation between the two pairs, the delta Q and Q. Okay, and so again, using the same logic, I can write down a topological term that corresponds to this. So this only involves the translation gauge fields because it's only the translations and the charge conservation symmetry that protects the wild points in this case. So this is what the term looks like, and this is basically the mirror image of the topological term for the magnetic wild semimetal, where I just interchange the translation and the electromagnetic gauge field. I interchange Z and A. Okay. And so, well, you can find this momentum from the fact that the temporal component of the translation gauge field couples to the charge, which is the momentum, right? Couples to the translational symmetry charge, which is the momentum. And so a non-trivial consequence of this action is that there is again a fractional charge on a screw dislocation with a dislocation line along Z. So the analog of the fractional charge on a 2 pi flux line here is the fractional charge on a screw dislocation line. And so this again is in principle observable. Okay, well, how much time do I have? You're muted. I can't hear you.
Sorry, you're reaching half an hour, which is scheduled time.
Okay. Well, yeah. So maybe then, yeah, I should not really talk much about the second half, unfortunately. Let me just mention the result. So basically, what I've shown in the first half, in the first part of this talk, is that unquantized anomalies, and they're unquantized because the coefficient of the anomaly, this nu, right, which is related to the separation between the nodes, is of course continuously tunable, right? But so the unquantized anomalies imply gapless modes in the presence of weak interactions. The question you can ask is, does this remain true when the interactions are not weak? And well, interactions, of course, may always simply tune the coefficient of the anomaly, since it's unquantized, to a trivial value by simply, let's say, in the magnetic wile semimetal, by simply moving the wile nodes to the edges of the brilliant zone, or to the center of the brilliant zone. So we really need to fix the coefficient of the anomaly to make this question non-trivial. And so in particular, the question that we ask is can we gap out wile nodes in a magnetic wile semimetal while keeping the Hall conductivity fixed? Okay, while keeping the Hall conductivity at a fraction of E squared over H times the reciprocal lattice vector. Okay. And so, well, surprisingly, the answer to this turns out to be yes, but one particular separation between the wile nodes, which is exactly half a reciprocal lattice vector. Okay, and well, I don't really have time to describe how this works. So basically, yeah, so chiral anomaly turns out to be consistent with a gapped fractionalized state at one particular value of the wile node separation, and the state that's realized in this case is an analog of the fractional quantum Hall effect, but in three dimensions. And well, we establish it by a method called vortex condensation, where we induced a gap superconductivity first, and then disorder the superconducting phase without closing the gap by proliferating vortices. And so this produces an insulator, but the anomaly places some restrictions on this procedure and prohibits a simple insulator. But allows for an insulator with a particular type of topological order, and only when the separation between the wile points is half a reciprocal lattice vector. And well, so let me skip all the details of this. So basically, the observable consequence of this would be something like this. So in a non-interacting magnetic wile semimetal, basically, if I tune, let's say, the magnetization, which tunes the separation between the wile points, the magnetic wile semimetal, as you know, is an intermediate phase between an ordinary insulator with zero Hall conductivity and an integer three-dimensional quantum Hall insulator, where the Hall conductivity is E squared over H times the reciprocal lattice vector divided by 2 pi. And as I tune the magnetization, I smoothly go between the two states, right? This tuning of the magnetization is kind of the analog of tuning the magnetic field in the regular two-dimensional quantum Hall effect, where you drive the plateau transitions by this. And so the prediction is that with strong interactions, this smooth evolution may be interrupted by a plateau, where the value of the Hall conductivity is quantized to exactly half of this integer value. Okay, and so the state that's realized here is basically an analog of non-abelian even denominator fractional quantum Hall states in 2 dimensions, but generalize non-trivially to 3 dimensions. Okay, so well, let me stop here. So these are my conclusions. So basically, what I've shown is that topological semimetals may be characterized by unquantized, meaning having tunable coefficients, anomalies. These anomalies may be expressed as topological terms, which involve electromagnetic as well as crystal symmetry gauge fields. So like translation and rotational symmetries. Now, what these topological terms describe is basically fractional electric charges induced on symmetry defects, such as flux lines in magnetic wire semimetals, dislocations or disclinations in the time reversal invariant wire semimetals and the Dirac semimetals. And finally, the part that I didn't have time to talk about is that chiral anomaly in the magnetic wire semimetal is actually consistent with a fully gapped fractionalized insulator when the separation between the wire points is exactly half of a reciprocal lattice vector, which is a non-trivial generalization of the fractional quantum Hall liquid to 3 dimensions. So thank you.
Thank you, Anton. So we have time for a few questions. Let's see.
I have maybe, oh, hi.
Yeah, please, go ahead.
Yeah, so can you make any statements using your rotational gauge field action about the gapability of Dirac semimetals on curved manifolds?
Yeah, I'm not sure about curved manifolds. We can actually make some statements about gapability of Dirac semimetals for particular non-trivial values of the separation between the Dirac points. So
I was just thinking of, if you think of a closed curved manifold as, flat space with a certain number of disclinations.
Right. Well, so maybe I guess I'm still not understanding the question. So as I was saying, this actually does predict that Dirac semimetal can be gapped. You can get a trivial insulator for certain fractional, for certain separations between the Dirac points, and the simplest one is just a half of a reciprocal lattice vector. So in this case, there is actually no anomaly here, and you can gap out a Dirac semimetal and get a trivial insulator. But there is in fact a whole set of these separations that's discussed in our paper.
Okay.
Now, yeah, I have not, to be honest, thought about curved manifolds.
Okay.
Yeah,
thanks.
Maybe I can comment briefly on that. So Barry, if you look at this term, if you neglect the fact that it's you only have discrete C4 symmetry, if you pretend that you have continuous rotation,
sure,
then that C4 wedge dA is nothing but the Wen-Z term.
Wen-Z term,
So
right.
it's basically like a discrete version of Wen-Z term.
Right.
So the wedge,
that's what
the wedge Z is basically you stack that in the Z direction. So so there are some similarities there.
So there's some kind of discrete shift.
Yes. Yes.
Okay.
I think we have a question from Jaakko Jisinen. Can I unmute yourself?
Yes, can you hear me?
Yes.
So did you consider any terms that would not feature the electromagnetic fields, but instead be basically composed of just the crystalline?
Sure. Yeah, you can also have terms that involve on the crystal symmetry gauge fields. I mean, the problem there is that it's hard to get anything observable from that, right? The advantage of such mixed term that involves at least one electromagnetic gauge field is that you actually get at least a potentially observable quantity, the charge, the electric charge on a defect.
Right. So
if you have only crystal symmetry gauge fields, it's not clear what observable quantity you would get from there.
right. So I would expect perhaps momentum or angular momentum curve.
Right. Yeah.
So basically-
Right. But that's difficult. Momentum is not even a gauge invariant quantity really, and well, angular
Not
momentum.
in the crystal, yes.
Yeah, angular momentum maybe, but it's yeah, it's difficult to measure.
Okay, thanks.
I actually have a question. Carl, please go ahead. I'll ask it later.
Hi, thanks for this very interesting talk. I have a question. I find this notion of unquantized anomaly, can you explain? Because usually, I mean, the way we think about anomalies is something, you know, which is very stable. The non-renormalization theorems, you wouldn't expect that you can.
Right.
So.
Right. Well, so the unquantized again simply means that this coefficient here, which, well, let's talk about the simplest case of just the magnetic wire semimetal. That coefficient is just related to the distance between the wire nodes, right?
Mm-hmm.
And that's obviously not quantized. It can be anything. That separation can be anything from 0 to a reciprocal lattice vector. It's unquantized in this sense.
Okay. Okay. Thanks.
Is it possible that that this unquantized anomaly somehow originates from a higher dimensional quantized anomaly?
Yeah, that's right. That's right. So you can also think of it in this way. You can think of let's say these two wild points, the wire symmetal in 3+1 dimensions as being a boundary of a 4+1 dimensional quantum hole, of a 4+1 dimensional insulator, right? And so right, and so this coefficient is simply the charge of the translation gauge field that enters into that 4+1 dimensional action, with the 4+1 dimensional term, right? And that charge again, this charge is the momentum, and it can be can take any value within the first brilliant zone. Yes.
Thank you. So you basically plug in something unquantized into a higher dimensional anomaly, and you get
yeah, you plug in something that has a continuously tunable charge into a quantized 4+ dimensional anomaly, and then on the boundary you get an unquantized.
Yeah, that's what I thought.
Yes, that's right.
Thank you.
Dilshad?
I have a simple question. How does the C4 term look like? I mean, is there expressions for the C4?
Well, so C4 again, this is a rotation gauge field. I mean, it's basically defined by this property that a line integral of C4 along a closed loop in your crystal gives you the number of these disclination lines that cross this loop, right?
Oh, I see. Okay, thank you.
I have a quick question about the last part, the fractional part. What determines the width of this plateau?
Well, it's the size of the gap, right? And that of course is a non-universal thing, right? So that depends on the specific realization, microscopic realization of the state. We didn't actually provide a microscopic Hamiltonian, right, of a, let's say, while semimetal or a lattice with some interaction that actually gives this state. We just showed that this state is possible. Okay, so the width of this plateau is a non-universal thing that depends on actually the magnitude of the gap in that state. But what is universal is the value of the whole conductivity.
Yeah, I guess my question is, what guarantees that this is not infinitesimally small and is observable? Is there anything?
Nothing guarantees it, right? So again, we have not actually provided a specific Hamiltonian that would realize that state. Okay, we just showed that the state is possible. That's already a non-trivial statement, because basically only this. So if you say that, so I want to gap out while nodes without breaking any of the symmetries that protect the while points. That's the question we are asking, right? And while keeping this a non-trivial value of the whole conductivity within those two quantized values, 0 and E squared over H times the reciprocal lattice vector. This is only possible for this particular value.
Thanks. Maybe last question by Baptiste.
Yes, thanks. Just a trivial question maybe, but during all your talk, there is this z direction, which is always given as fixed as the z direction. Right. What is special about your z direction in all this talk? Well, how did you separate it from the other direction? I mean?
Right. So this is just well, in the case of the magnetic while, I have I actually have magnetization that points in a particular direction, right? And so then, well, in the simplest case, when you have just two while nodes, they are separated in this direction.
Oh, fine, thanks.
What peaks the direction. So same happens in a Dirac semimetal. In that case, there is a rotation axis, right? And the Dirac points are separated along this rotation axis.